welcome to Mathematics with Tom. I am Tom, and today we're going to look at a driving frequency and a frequency response when we're studying the second order differential equation that models the behavior of a spring. Well, what we did is we originally solved this problem. M, this mass of the spring, so M times y double prime plus k times y equals 0, and we said that our solution to this was y equals, and actually I'll just be careful, is that y null, because that's just a null solution. So y null is equal to c1 cosine of omega t plus c2 sine of omega t. And what we also found in the process of this is we found that omega is equal to the square root of k divided by m. That's right, the spring constant divided by m. And so then this would obviously imply that omega squared is the same as k divided by m. And what I'd also like to notice in this problem is this. Well, because we're going to solve this problem. M y double prime plus k times y. Now we're going to have some driving frequency, some cosine of omega t. And at this point, we need to be very clear on our notation. And that is this. Notice that I've introduced an omega, but this is different than the omega from the null solution. So I'm going to go put an n for the omega natural or the omega null in all of my solutions regarding the null solution. And there we go. So fix all those. Now we can look at this new this new harmonic frequency omega. And we're going to make an educated guess that our solution will involve cosine times some scalar. So we're going to try some y particular that's going to just have some scalar capital Y times the cosine of omega t. And what we're going to do is we're going to solve m y particular double prime plus k y particular equals cosine of omega t for capital Y. We're going to find out what capital Y is, and then we will have our particular solution. So let's try that. Well, let's find y particular prime. That's going to be a minus omega, capital Y, sine omega t. And if we continue, we need a second derivative, so y particular double prime, that's going to be a minus omega squared capital Y cosine of omega t. All right, let's substitute. We're going to substitute these values into this equation and see what we come up with for our y. So I have m, I'll write it this way, m times minus omega capital Y, omega squared cosine omega t plus k, parentheses, plus k times y particular, which is capital Y cosine of omega t. And this has to equal 1 cosine of omega t. Now, I'm going to factor out a y on the left-hand side. So capital Y times, we'll put whatever is in here, and then we'll have our cosine of omega t. So really, we're going to have 3 factors here, equals the right-hand side, 1 cosine omega t. Well, if I factor this out, what do I get? I get a minus m omega squared plus k. And if I take this one more step, since the cosines, these are already the same, these are exactly the same, that just means that 1 has to equal capital Y times this product. So capital Y times, and let's just write it in a more natural way, k minus m omega squared squared has to equal 1. And then let's solve that now. So I can say that capital Y is equal to 1 over k minus m times omega squared. So our solution, y particular, is going to be capital Y, k minus m omega squared cosine omega t. It's now capital Y is the frequency response. The frequency response to the driving frequency. The driving frequency cosine omega t. So cosine omega t is putting some input into our function. When it comes out, our conclusion is it's going to come back out also as a cosine, but it's going to be adjusted. That adjustment is our frequency response. But notice this, our frequency response is very simply just a fraction, and you always need to be concerned about 0, so let's be careful about that. So let's look at our frequency response, capital Y. And let's factor out an m. You'll see why. If I factor out an m, then I'm going to have k over m minus omega squared. Oh, but look at this. This is where we opened earlier today. We said that k over m is equal to the natural frequency squared. So if I use that and rewrite this, we can say our frequency response is 1 over m times the natural frequency squared minus the driving frequency squared. And so we're going to write our solution that way. Our y particular is equal to the cosine of omega t divided by m times the natural frequency squared minus the driving frequency squared. And the question you should be asking is, what happens when the natural frequency is equal to the driving frequency? I hope that helps, and thanks for watching.